So a lot of different integration techniques in section 8.1, mostly U-substitutions. We'll start with problem number 12. The integral of the secant of 5x times the tangent of 5x dx. Now, we'll do this one out the long way in detail this time, but what I encourage is that you get pretty good and you can start doing some of this stuff in your head. All right, that you don't have to do the formal U substitution and do it in your head all the way. So this looks a lot like something we're familiar with, which, you know, we can make it look like something familiar if we do a U substitution. U equals 5x. du equals 5 dx. If we're playing the game that I usually do, which is to solve for what we have in the integral, we'll multiply both sides by 1/5. And now we can make our U substitution because we know what dx is. Dx is 1/5 du. So secant of u, tangent of u, times 1/5 du. You can take the 1/5 out in front, or maybe you can just integrate it from here. But what's the secant of u times the tangent of u integrate to? Just secant, right? 1/5 secant of u plus your constant. Last but not least, 1/5 secant of 5x. Yay. Nice. Now, moving forward, it's nice if you can kind of just play some mental games, say, okay, if I was differentiating, then that 5x would be a multiply by 5. But if you're integrating, then it's going to be a divide by 5. And that's essentially what we had here, is that term of 1/5 out in front. So I encourage you to try and get good at skipping some of these steps, doing something like that, because it's just really going to slow you down if you have to make U substitutions every time you run into something that's not picture perfect, like your integration tables. That's just a suggestion. Don't do it at the expense of getting something wrong, but I would suggest that. Onward. So problem number 20. Integral of 4x minus 2 over 2x plus 3 squared. Is it squared or cubed? Squared. All right, so I got it right. Any ideas on what to do to integrate this one? Yeah, you can break it up. So integral of 4x dx minus integral of, well, we got this thing here. Any suggestions? Yeah, eventually U substitution. 2, I guess what I would do is this. I'd write as 2x plus 3 to the negative second power dx. And writing it with a negative exponent is going to allow us to integrate it, especially after you do a U substitution. Now the first one's just going to integrate to 2x squared minus 2 times all this mess. Don't worry about the constant of integration until you're all done, because we only need one constant of integration. Andrew, what should we let our U substitution be? U equals it's a 3 in case it's not clear. Some help? It's Andrew, isn't it? Andy. I'm sorry. Andy. Yeah. 2x plus 3. So du is 2 dx, or 1/2 du equals dx. All right, so we get u to the negative second times 1/2 du. These cancel each other out. 2x squared minus the integral of u to the negative second du. So that's nice. Make sure that when you're all done that you get back to the original unit. I don't want anyone leaving me with units of u here, for instance. 2x squared plus u to the negative first power plus your constant. Yeah, that's right. Last but not least, that's 2x squared plus 1 over 2x plus 3 plus your constant. Yeah, please. I'm not sure how I'd apply the chain rule here. Chain rule would apply with multiplication or differentiation, not necessarily integration. Although there is kind of a product rule that we'll get later on. It's called integration by parts, but that's a little bit later in chapter 8. Some more. Let's keep going. Let's do problem number 28. Gave that one a little bit of a build up. So let's get around to 28. Revisit our buddy Pascal. I believe it was Pascal who at one point during his life was told by a doctor that he was living too kind of Spartan of a life. Basically, he was told to go out and party it up for a while, and he did. He embraced that advice very enthusiastically. He did kind of retire from mathematics for a while, and I think he went into religion. And there's something, if you want to look it up, called Pascal's wager, which is kind of an interesting little bit, but I'm not going to go into that here. We are going to use his triangle, Pascal's triangle. So that's going to be 1, 1, 1, 1, 2, 1. And you should make sure that you can come up with the first few levels of this triangle. I'm not going to go any deeper than 4, I'm sure. But you should be able to find those levels. And of course, these are going to be the coefficients for various things like a plus b to the 4th power. So the way that works, if I were to expand this, I would expand this and say, all right, I'll have a to the 4th, a to the 3rd, a to the 2nd, a to the 1st, and then a to the 0. And now, with the b's, I'll do likewise. B to the 0, b to the 1st, b to the 2nd, b to the... I missed one here. B to the 2nd, b to the 3rd, and finally b to the 4th. Man. All right. Photoshop. There we go. B to the 0, B to the 1st, B to the 2nd, B to the 3rd. And then b to the 4th. Now, these numbers here are the coefficients of that polynomial. So this is going to be a 1 here, plus a 4 here, plus a 6 here, plus a 4 here, plus a 1 here. So whenever we have something in this form and we expand it, it's going to follow along with that pattern. What's that mean for a problem like number 28? Well, it's the integral of x times... I'm going to change this. I'm going to bump it up a little bit to make it worth our time. If it was just a square, like they have in the book, 2 over x squared, then it really wouldn't be worth our time. So let's step it up to maybe a 4th power, like we just did. If you're stuck doing something like this, you're probably going to want to expand it with Pascal's triangle. So how would that look? It's going to be x times, well, this is your a, and this is your b. I'll have 3 to the fourth power, and let's leave ourselves some generous amount of space here, plus 3 to the third power times 2 over x to the first power. I'm still going to have to go back in and throw in some coefficients. But what's going to happen is that the power on the 3 is going to keep on decreasing, so 3 squared. The power on this term is going to increase, 2 over x squared. What's the next term going to be? 3 and 2 over x cubed, and finally 2 over x to the fourth power, all dx. I still need to stick in those coefficients. Those coefficients come from Pascal's triangle, so a 1 here, which you don't typically really need to write, I will just for completeness, a 1, a 4, a 6, a 4, and a 1. It's a lot better than trying to expand this thing by hand. Can you imagine trying to multiply that by itself 4 times, collect all the like terms, add them up? No, thank you. So, the integral of x, that's going to be 81. 4 times 27 is 108, plus 108 times 2 over x, plus, that's going to be 6 times 9 is 54, times 4 over x squared, plus 12 times 8 over x cubed, plus 16 over x to the fourth. So, last but not least, let's distribute the x and also multiply these things together. I'll get the integral of 81x plus 216, yeah, just 216, right? Because that x and this will cancel. Plus 216 plus 216 again, right? 216 over x. Instead of writing over x, I'm going to write x to the negative first plus 96 x to the negative second plus 16 x to the negative third, like that. And now that it's expanded, it's not too bad to integrate this thing. Actually, it's hopefully pretty easy. So it's going to be when you multiply the x times here, one of them will cancel. So that's where that negative third comes from. So 81x squared over 2 plus 216x. How about this one? What's that integrate to? Not just 216. Right? No? Vicky? I don't know. 216 natural logs. Yep, 216 natural log. 216 times the natural log. Yep, well done. Minus 96x to the negative first. Minus 8 x to the negative second. Plus a constant. Whew. But the thing that I'm trying to get across here is how to use Pascal's triangle to save yourself a ton of work in a problem like this. Multiplying that out by itself 4 times, no thanks. Yeah. What's that? Calculator, not too many calculators are going to do that because it has the x. Yeah. So. Okay. Let's keep going. Some more. And basically what I'm trying to do and show you is as many little tricks as possible. But I'll give you a heads up. I can't show you every trick that you're going to need. There's going to be some in there that you're like, oh, how did I do this one? You didn't show us this. Well, I can't. I mean, I have to do so many more problems, but I'll try and show you as many as I can. Yeah, that's what's going to separate, you know, a class like this from some of your lower level classes. Is that sometimes you got to move out beyond the lecture a little bit. Problem 38. Let's step over to trigonometric functions for a moment. 1 over cosine of theta minus 1 d theta. It looks a little dicey. So let me give you a hint. We're going to rearrange our integral by multiplying by 1. But you can't just choose any form of 1. Does anyone know? Anyone? Close. Not minus 1, plus 1. Plus 1, because plus 1, now you're multiplying conjugates. Just as a quick reminder here, a minus b times a plus b. When you multiply conjugates, and I'm not going to FOIL it all out for you, it's going to be a squared minus b squared. So that's nice, because in the denominator, I'll get some nice simplification. I get the integral of cosine squared of theta minus 1, and the numerator I'll just get cosine of theta plus 1. All right, well, does that help me out at all? Yeah, actually, it kind of does. Let's see what we can do from here. So in the denominator, I'm going to factor out a negative, and let's see. Where do I put? I'll just put that right out in front. So it's going to be 1 plus cosine of theta over 1 minus cosine squared of theta d theta. Now, does this help at all? Well, yeah, we can do something here. That's sine squared. So 1 plus cosine of theta over sine squared of theta d theta. Now, sometimes people will try and apply this in the wrong direction. So let me pause for a second. If you have a plus b divided by c, you can split it up as a over c plus b over c. And that's fine. What you can't do, and what I see people do a lot, is this. If you have a over b plus c, you can't split that up as a over b plus a over c. It doesn't work that way. It only works when this thing is on the bottom. But that's all we need here. So I can split that up as negative of the integral of 1 over sine squared theta d theta plus actually minus the integral of cosine of theta over sine squared of theta d theta. Now, one of these is something that I probably wouldn't hit you with very often. Cosecant squared of theta d theta. But the other one we should be able to do. Slav? Good. U-substitution. So what would we do for U? Not quite. Just sine. Yeah, just sine. So right here we could let U equal sine of theta, du equals cosine of theta, d theta. And that's perfect because that's exactly what we have. So it's going to be minus du over u squared. So we've come a long ways. At least we're in a position to find some antiderivatives now. This one, a little obscure. I'm not sure I'd ask you to remember that one. It's minus cotangent of theta. How about this one? How's that going to integrate? Not an ln. It'd have to be the first power to be an ln. So I guess the way to think of that part down there is it's u to the negative 2. So you add 1 to the exponent and divide by that same exponent. We've got a lot of cleaning up to do here. Let's throw in our constant before we forget it. Cotangent of theta. The negative and the negative cancel. What about u to the negative first? What else could I do with that? Bring it down in the denominator. And finally, I don't want an answer that has a u in it. Cotangent of theta plus 1 over, what do we do? Sine of theta plus c. The other thing I would accept is the cosecant of theta. I'd be curious to see which one Wolfram alpha gives you. I would imagine they would give you the cosecant. But I'd accept either one of those there. Couple more tricks. Let's look at problem number 24. There's a trick in there that I want you to see. Integral of 3x over x plus 4 dx. We're going to see a little bit more of this later, so maybe seeing a little bit of a foreshadow. But anytime the degree of the numerator is greater than or equal to the denominator, you want to do some long division. You want to divide it out. Now in this case, if you actually know synthetic division, you can do synthetic division, that's fine. But if you're dividing by an x squared or something like that, you can't do synthetic division. Synthetic division only works for x plus something and x minus something. We could do synthetic division here, but let me just do it longhand. X plus 4 into 3x. What do you multiply this by to get the 3x? 3. 3 times that gives you 3x plus 12, but then you have to subtract it, and you end up with a minus 12 as a remainder. So this is 3 minus 12 over x plus 4 dx. Now earlier I said, well, you know, it's really great if you can do some of these things in your head. This is not a perfect logarithm. If you had to substitute in order to integrate this, you'd probably let u equal x plus 4. What does that tell me about du? Du equals dx. If du equals dx, that's the best it can get. That means it's almost a one-for-one substitution, and you should do that one in your head. So in this case, doing this in our head, that's going to be 3x minus 12 times the log of x plus 4. Done. So if du equals dx, just kind of bypass that u substitution stuff. Just do that part in your head. Integrate it like you think you would. Let me give you some hints on some of the homework rather than spend time doing another problem. So let me give you some hints. On problem 23, you know, part of the reason I do the odd problems or even problems in class is so that when you go home and you're stuck, sometimes you can look back at what we did and say, oh, okay, yeah, I know the trick from that one. So the trick from 23 is to divide first, just like we did in problem 24. Problem 25. Here's your u substitution. Let u equal 1 plus e to the x. Problem 33. Multiply by e to the x over e to the x. Now, what's going to happen is if you're careful in working with the exponents, you should cancel out the negative exponent that they have in that problem. And last one, problem 37. Let me just take a look at that one. Try to remember what the trick is there. Yes. So you've got a 1 plus cosine of alpha over sine of alpha d alpha. What you should do is split that one up. Split it up as 1 over sine of alpha plus cosine of alpha over sine of alpha. And then you should be able to integrate it from there. For homework then, try 7 through 51 and 57 through 65. Just the odds. And that's section 8.1. That's as much as I got time for today. I can maybe do a couple problems next time. And if you have any questions on the homework, then let me know.